Hey guys, welcome back to the dynamics video series we have going. Today's video is going to be about special points or special point approaches to these problems with all these rotating bodies and stuff. So with special points, I think it's a little easier than vector loops, which was the last video. We're essentially just picking points to do, and then using the equation that we know to actually solve them all. So let me write down the equation first things first, right? Because it's going to be on your cover page, so we can just write it on the paper. Let me pull it up. So the equation is, right, I haven't read the problem yet, but that can wait, it seems, that the velocity vector of some point equals the velocity vector of some other point, right? These points are on the same body, plus the angular velocity of that body with the cross product of the position vector for these from the first body or the first body to the second body, and then plus any relative velocity, right, between these 2 points. All right, so I think it's easier to explain this equation in a problem, so let's go ahead and get started. So the slanted green and vertical black sticks are 1.5 meters long. The red horizontal stick is 2 meters long, so let's label that. So these are each 1.5 meter, and this one 1.5, and this is 2 meters. Okay. The angle is 20 degrees. This is in vector loops. We don't need to use these angles. We can actually just get rid of that and label it off the jump because we're talking about at this point in time. And then the end of the black stick is pulled to the left at a constant 4 meters per second. What is the angular velocity of all 3 sticks, right? So this blue velocity term, I'm just going to write it as 4 meters per second. Right? And that applies to this point right there. Okay. So this is all we're given, right? And we got to figure out the angular velocity of all 3 of these sticks. So the first one I'm going to try and do, and always try and do this, is the easiest one so far, is to do it first for this black stick, right? Why do I see I can do it for the black stick first pretty easily? 2 things. It's because it's going to be using the shortcut. So let me write that, shortcut. All right. So I don't know if we've gone over in lecture yet. He should soon if he hasn't already. The shortcut method, right, is it's really easy to find the angular velocity or the length of something if you know 2 of the other variables, right? The criteria for using the shortcut method is that one point, right, one of the points has to be a fixed point. One point is fixed, right? And the other one, it doesn't have to be fixed, but we have to know 2 of the criteria, right? So we have to know a velocity and a distance, or a velocity and an angular acceleration, or a distance and an angular acceleration. And in this case, we know that the velocity of this point over here is 4, right? And that the distance of this black bar is 1.5, right? And since that's true, we can write this equation where the velocity of that point is equal to the length of it, so the distance, so the length of this black bar, times, and then this is just a normal product, not a cross or a dot, the angular velocity, right? So this angular velocity of that black stick, right? Let me label all these points before we get too far ahead. So I'm just going to say this one's A, this one's B, this one will be C, and this one's D, just basically arbitrarily. So that means that this is the velocity of B. Cool. So let's plug in what we know. So we know velocity of B was given as 4, right? So I'm just going to write 4. And that's equal to the length of the stick, right? And the length of that black stick is 1.5. And that's times the angular velocity of the black rod. All right, one equation, one variable, we can just solve. So our black angular velocity is equal to 4 over 1.5. Or just about, what is it? Like 2.66. We'll just say 6.7. I think it's 2/3. And that is radians per second, right? And then we still need a direction for this, right? Because you can't just leave it like that. So let's see in which way this is rotating. I'm pretty sure you can tell, but since this arrow is going this way, that means that this black rod is rotating like that, right? Which is the counterclockwise direction. So this has a counterclockwise direction. And that's actually one of our answers, right? So that's it for the black stick. So I'm just going to highlight it. All right, so that was a shortcut. Can we use a shortcut for the other two? No, right? For this green rod, which is the only one with a fixed point, the only one we can look at for even possibly using a shortcut. We only have one of the values, right? We only have this distance. We don't have the velocity of this point or the angular velocity of the stick, right? So no shortcut there. So we're going to have to start using our equations. So let's do that. So let's do it first. I'll say for the red stick, just arbitrarily. So I'm going to be writing this equation, but for the red stick, right? So I'm going to pick 2 points. It's important to pick, and I guess it's going to save you time doing algebra, to pick which point you want on the left side, right? The one by itself. In this case, I'm going to use C for both of my equations because C is a shared point between these two sticks, right? And since it's shared, if I just equal it to each other at the end, it'll make the algebra a lot simpler. So let's do that. So let's say I'm doing point C, right? And this is equals, and then what's the other point on this rod? Point C and point B, right? So that's going to equal the velocity vector of B plus the angular velocity of the rod they share, right? So they're sharing the red rod. So I'll just denote that with a R. And then times the cross product of the, what's it called, positions from where to where, right? So it's between these two, but is it from B to C or C to B? It's always going to be from the one that's on the same side. So it's going to be B to C, right? So the one that you're on the same side as you're writing this, the right side of the equation, it's going to go from right to left. So it's going to be from B to C here. Now, since these are vectors, it is important that you go from B to C, not from C to B, because it's going to change the direction of the vector, which is going to make your answer incorrect or just opposite sign. So yeah, that is important. And then plus any relative terms that may be appearing. All right, so let's start filling this in. So velocity of C is still unknown, equals velocity of B, which we did figure out, right? We said it was given up here. So this is a vector, so we do have to denote the direction. So let's write our I and j unit vectors. So I'll write it here. So let's say to the right is the positive I, and then up is the positive j. Okay. So let's look at this vector in B. It's going in the I directionality, right? Left and right, but it's going to the left, so that's a negative I. So this 4 is going to be negative 4 in the I. Okay. And then plus whatever the angular velocity of the red thing is, that's what we're looking for. So we kind of just leave that alone for now. And let's just assume it's in the positive k direction. Okay. And then times the cross product of the what's it called? Position vector here. So as we go, you can imagine from B to C as just walking, right? So let's say we're walking across this red beam from B to C. What are we doing? We're traveling in this direction, which is the positive I, and we're going a distance of 2 meters, right? So this is going to be a positive 2I. Cool. And then this last term is the rel term, right? So what the rel term is saying is as this thing is spinning or at all in this thing, are B and C getting closer together relative to each other? The answer is no, right? Because the bar is fixed length, right? So B and C are always going to be that 2 meters apart no matter how it's oriented. So that's just going to be a 0, right? And if it's a 0, we can just leave it out. So let's just get rid of it. And then let's just rewrite this to make it more simple. So VC equals negative 4I plus, and then whatever this cross product is. So at this point, it's good to remember either one of two things, that K cross I equals J, and K cross J equals negative I. You can either memorize that, or you can do this little thing where you have I, J, and K, right? And then do a circle like that. And then what this tells you, this circle is the positive direction. And if you're going from K to I think this circle is actually on your cover page. If you're going from K to I, that's positive J. And if you're going from K to J, right, so K cross J, that is going in the opposite direction of this arrow, right, this big circle arrow. So that's a negative I, right? So either one is okay, now just to remember. So let's see what we do. So now we have WR times 2, right? So 2WR, oh, let me keep it red. 2WR. Yep, 2WR. And then this is a K cross I, right, which is a positive j, so it's just j here. Okay, cool enough. And then that's that whole term. So let's move on. So that's the red bar. Let's now do this green bar, right? So I do this green bar in green, just maybe keep the colors consistent. So when I do the green bar, I'm going to talk about point C and point D. I'm going to try and keep point C on the same side as the other equation, right? So I can just equate these two things to each other at the end. So VC equals the velocity of D, and then this same equation, right? So plus the angular velocity of the bar they share, which is the green bar. And then the cross product of their position vectors, and then we're going from D to C. So D to C, right? Plus any relative velocity they have to each other. Easy enough, so we can fill these in again. So our velocity of C is unknown, right? Our velocity of D is known, even though it's not explicitly stated, right? We can see that D is here on a fixed point, right? It's on this fixed support. So the velocity of this point, right, that's on the support, obviously is 0, right? It's not going to be moving anywhere anytime soon. So the velocity there is just going to be 0. And then plus, we can write this in. So this is WG, and we don't know the directionality of the spin, right? So let's just assume it's positive K. And then cross product of this distance that we have to walk on this green bar, right? So we can actually decompose this distance into two distances, right? One in the J and one in the K. So we have that horizontal distance and then this vertical distance, right? So this is the time we're going to use our angles. So since this angle is 20, we know this angle here is also 20. And if that's 20, then this is the cosine of 20, and this is the sine of 20. Okay. So it's going to be our 1.5 times the cosine and sine of 20 in the I and the j. So this is going to be the positive I, right? This direction, plus I. And then since we're going down here to get from D to C, this will be a negative j, right? So those will be our two directions. So first we write the I term. So it's 1.5, and that was the cosine of 20, and that's the positive I. Oh, that's not j, I. And then we're going down, so it's negative 1.5 sine of 20, and that's in the j, right? Cool. And do we have any REL terms? Answer is no again. It's the same as the other bar, since these points C and D are not getting close to each other or any closer any farther. They have a relative velocity of 0, so we can either do plus 0 or we can just exclude it, right? So I'm just going to leave it out. I'll just take out this one too while I'm at it, and then move this over. Okay, that's cool. And now let's do the same thing we did last time and simplify it, right? So VC is equivalent to, just more, get all the constant terms out. So this and this, constant terms. 1.5 WG times the cosine of 20, right? And then K cross I, that is a positive J, right? So positive. I'll write it out. And then we have negative 1.5 WG times the sine of 20. And then this is now K cross J. And we know K cross J is negative I. So I, and then this thing flips sign. So now instead of negative, it's positive. Okay. Cool. Continuing on, we have these two equations, right? So we notice one thing that we did intentionally is keep this side and this side, right? The left and the left of both things as VC and VC, right? So these two equations are equivalent to each other. And since they're I and j components, these are vectors, we know that the I of the red equation is equal to the I of the right equation, right? The green equation. And then the j's and j's are equivalent in these as well, right? So we can actually just break it up now into components. So in the I component, right, I have this term right here. So I have negative 4. And that's equal to the other I component. So this term over here, which is 1.5 times WG sine of 20. Okay, easy enough. And then in the J component, I have the other term, right? So I have this J term, 2WR in the J. Oh, I don't have the right J. because I'm writing that here explicitly, is equivalent to this j term, which is positive 1.5 wg, that's a weird g, wg cosine of 20. And then that is there, and I think that about solves our problem. All that's left to do is algebra. So let's see, we have these two equations, right? So we have 1, 2, and we have how many variables? 1 and 2. So 2 equations, 2 variables. This is solvable with algebra. You can either do it by paper, do it by hand, or you can use Mathematica. I elect to always use Mathematica just because it's easy, right? And so when I do that in Mathematica, I get two things. I get that WR is the same thing as negative 5.49, right? Which means since it's a negative, it's going in the clockwise direction. So it's just 5.49 radians per second, right? This is a velocity, an angular velocity, in the clockwise direction. And then the green one, I get from this that this is negative 7.79 about, which equals, same thing, 7.79 radians per second, again in the clockwise direction. All right, so this way, this way. And I think that just should be our answers, right? So this thing asks for 3, what is it? Angular velocities, and we got all the angular velocities for the 3 sticks. And that's going to be about how you solve this problem, right? So just remember that when you're solving it, be very particular about how you're orienting your stuff. Make sure you're adding and multiplying with the cross product in the right way. And if you can use the shortcut, use the shortcut. It saves a bit of time, especially on exams. That's going to be it for the video. Bye.